the object I want to talk about today is high-rank Teichmüller theories. And this ties well with the seminar that Olivier gave yesterday at the BOURBAKI seminar. But I will start recalling some of the things we heard yesterday, because the audience seems pretty different. And so I hope that the people that were there will not get mad at me, because I'm repeating stuff that you now know very well already. But I want to put a slightly different emphasis than the one that Olivier was making yesterday to tie better with what I'm going to say later. So I want to talk about high-rank Teichmüller theories, but first let me start with the old story, which is Teichmüller theory. And to do so, I want to do an historically non-correct account on this theory, because I want to, rather than talk about Teichmüller theory, I want to talk about Fricke theory. So I'll start with SG, which is going to be a closed oriented surface of genus G, bigger or equal to 2. And or a curve if you're an algebraic geometer, complex curve if you're an algebraic geometer. So closed, connected, oriented G bigger or equal to 2. And for me today, the Teichmüller space will be the space of marked hyperbolic structures on SG modulo isotopy, which means that it's a not so hard exercise in hyperbolic geometry to show that as soon as I assume that the genus of this surface is bigger or equal than 2, I can find hyperbolic metrics, Riemannian metric on this surface that has constant curvature equal to -1. And a very interesting object to study is the space of all these marked objects, or all these marked metric. So mark means that I remember that these structures are really on this surface, so I know who's the fundamental group. And this is a natural equivalence relation that makes this space finite dimensional. And actually, Olivier yesterday, taking the perspective of complex structures on this surface, already observed that this is diffeomorphic to r to the 6g minus 6. And this is the equivalence relation that's needed to get a finite dimensional moduli space.
So L-manifold is like the infinity sense and isotopy the infinity sense?
Right, exactly. That's correct. So that's what I want. And right. And also, this is, if you are more an algebraic geometer, you should think of this object as the universal covering of the moduli space, Mg. So this is the moduli space of Riemann surfaces. But what this marking really does to me is to pass to the universal covering. So this is the quotient by the mapping class group will act on this Teichmüller space and give me this as a quotient. But for what I'm going to say later, it will be very important to remember what this fundamental group is. So remember this marking. And something else that comes out of this picture is that this is not only r to the 6g minus 6, but this is also as a natural complex structure. And by natural, I mean that I have a complex structure on this space that identified with c to the 3g minus 3, which is invariant for the mapping class group action, so that descends to this moduli space. This moduli space is a complex variety, and under this orbifold universal covering, I get the complex structure on this space. Right? So this is the object that classically has been very much studied, and maybe here I should add the word uniformization, which was behind what Olivier was talking about yesterday. But in order to get to higher rank generalization, I want to get a different perspective on this object, which is really by using the fundamental group of this surface. So now I'm saying that points in this space are marked Riemannian metric on the surface. And in particular, for any point, what is? Marked means that, this marked means that I'm fixing, mark means that it's on this surface. So I fix this surface as an abstract topological data, and I put hyperbolic structure on this surface, and I quotient by isotopy. But this means that somehow this marking tells me the fundamental groups of every point in this space is identified with the standard group object. Right, so let me get this standard group object. So I will denote for all my talk gamma G, the fundamental group of my base surface, my topological surface as G. This is a very simple group generated by A1, B1, up to AG, BG, with a single relation that given by the product of the commutator is equal to 1. And the way of thinking of this is looking at this space as actions on this fundamental group on H2. What do I mean by this? So if I fix a point SGH in the Teichmüller space of SG, then since H was a hyperbolic metric of constant curvature -1, I get that the metric universal covering SG tilde is the unique, complete two-dimensional manifold that is simply connected and has a Riemannian metric of constant curvature -1. This is nothing but the hyperbolic plane. So this gives me an identification of the universal covering of SG tilde with H2. And now, this means that to a pair SGH, I can associate an action of gamma G to the isometry on H2 by isometry. Right? So gamma G, the fundamental group of my surface, is going to act on SG tilde by deck transformation. And this gives me a homomorphism from the fundamental group to the group of isometries. And so this is going to be discrete and injective. Injective with discrete image. And this is going to be well defined up to conjugation. And what this is telling me is that I can think of this Teichmüller space of my surface as a space of homomorphism. So this gives me a map that's called holonomy from the Teichmüller space of SG into what I call character variety, which is set of homomorphisms from gamma G to PSL2R, which is this group of isometry. Where I mod out by conjugation. And the reason why I need to mod out by conjugation is because, well, this identification is not canonical, but it's canonical only up to composition with an isometry. Huh? So these are going to be, so by construction, all the homomorphism I'm going to get are going to be injective homomorphism that have discrete image. So with discrete image. And they're going to be co-compact then. I mean, as soon as this is going to be, as soon as you have an homomorphism that is injective and has discrete image, then it's going to be co-compact. Because that if the homomorphism is injective and has discrete image, you can take the quotient, and the quotient is going to be a surface that's going to then, by classification of surfaces, is going to be the standard surface that you look at. Right? So that's the co-compactness comes for free in this case. But this is not surjective on the space of homomorphism. Of course, this space on the right is much bigger. Right? And maybe I should add here a theorem of Goldman that Olivier described in detail yesterday that says that this identifies, and this is in the 80s, the Teichmüller space with a connected component of hom gamma G of my character variety that can be selected with a cohomological invariant. Which is this Euler class or this Toledo number that Olivier was talking about earlier. So what this means is that, I mean, in Goldman's thesis, Goldman proved that this character variety here consists of 4g minus 3 connected components that are selected by the means of this Euler number that ranges between 2g minus 2 and 2 minus 2g, and all the integer values in between here. And the Teichmüller space is really this extremal component. And can be, and what I want to remember out of this for today is that what I'm looking at here is a character variety of a countable group into a Lie group, such that there are, I mean, for which in the character variety, there is a connected component that consists only of homomorphisms arising from a very geometric picture. I mean, hyperbolic metric are very interesting geometric objects. And for me, these representations here are special in the sense that come from a nice geometry. And the higher rank Teichmüller theories is going to be about looking at similar instances for other different Lie groups instead of PSL2R. But before I get there, let me raise this. I want to make two more comments about the classical Teichmüller theory. So let me add two remarks that are going to be useful for the rest of my talk. The first one is a very easy observation that the group PSL2R, which is something that's not going to be valid anymore in a higher rank, which is that the group PSL2R, that's a group of isometries of H2, has various different incarnations. So this is not hard to check that this is the same as PO12. So PSL2R are the, projective classes of 2 by 2 matrices of determinant 1. But if you look at, instead of orthogonal matrices preserving a form of signature 1, 2, you get again the same group. This is an exceptional isogeny in low ranks. This is also equal to PSP 2R, because in dimension 2, preserving a symplectic form doesn't give me any condition. And this is also equal to PU 1, 1. So the group of complex 2 by 2 matrices that preserve an Hermitian form of signature 1, 1. And these P is really like quotienting by a finite center, so that I just really can talk about these isometries. But this gives me a lot of richness of this theory, of Teichmüller theory, that has been used a lot in the past 100 years, which is due to the fact that all these three groups correspond to different models of the same space. So this PSL2R acts on the upper half plane, which is the upper half plane in the complex plane, and that has the hyperbolic metric for which geodesics are either circles orthogonal to the boundary or vertical straight line. Instead, when I look at this, I think of the Klein model of the hyperbolic plane. This is inside the projective space. And when I look at this side, I look at so this is upper half. This is Klein. And this is the Poincaré model, in which geodesics are now, in which my model is the unit ball in C, and geodesics are going to be circles orthogonal to the boundary. But now this gives me a lot of richness to this theory, because I have different ways of understanding the same objects. This is sort of behind uniformization, that I can look at hyperbolic metric as complex structures, as well as real projective structures. And this gives a lot of different tools that you can pair together to get a lot of interesting results about this theory. So this is something that's not going to be true anymore in high rank, but I want to argue that we have a good replacement for these nice geometric features also in higher rank. So this was my first remark. And my second remark is something that I'm going to be very fast about, because Olivier discussed a lot this yesterday, which is a characterization of another characterization of point of hyperbolization, which is using boundary maps. So this is a fact that Olivier stated yesterday, that rho, a homomorphism from gamma G to PSL2R, is the holonomy of a hyperbolization if and only if there exists an equivariant monotone map xi from the boundary of gamma to the boundary of H2. And I want to tell you just briefly what I mean by this. So if you look at this model, you know what the boundary is. So this is H2. And here I have RP1, which is the boundary of H2, that I can also define in intrinsic geometric terms as sets of rays in my hyperbolic space up to parallelism. And now whenever I fix and now one can give an intrinsic notion of a boundary of my group, which will be identified with this boundary, whenever I fix a hyperbolization. And namely the orbit map is going to give me this equivariant. And you can, in a sense, if you want, you can just think of this, fix any base hyperbolization, and think of this boundary of H2 with the induced action on the boundary as a model for my boundary of the group. But this is another phenomenon that's going to play an important role in what I'm going to say next, which is in order to understand these geometric structures, it's very useful to go to infinity, where we lose uncertainty. I mean, everything is much more rigid at infinity, and this gives us important tools to study hyperbolizations. And these are the two ideas that I want you to keep in mind from hyperbolic theory to understand the higher rank generalization. Okay, so that, any questions so far? This brings me to point 2, which are higher rank Teichmüller theories. That from now on I will abbreviate by higher rank Teichmüller theories, HRTT. And in here, I mean, to tell you what I mean by this, I want to fix G, a semisimple Lie group. This will replace a PSL2R in my previous setting. And I want to think of this, as I was thinking up there, as to PSL2R, as the group of isometries of H2. I want to think of this as the connected component of the isometry of the symmetric space, and this is going to be a non-compact type. So G is going to be KL. The symmetric space X is going to be the quotient of G by a maximal compact subgroup. And this is going to be a replacement for the hyperbolic plane in the previous version. So this is going to be a Riemannian manifold with the big isometry group that has non-positive curvature. And now here is this rank that comes in my title, which is the maximal dimension of a isometrically embedded copy of Rn, max of the n, such that Rn in X is isometric. So now the difference between these non-positively curved Riemannian manifold and my hyperbolic model is going to be that here I have an interplay between hyperbolic geometry in some directions and flat geometry in other direction. And I will always look at groups of higher rank in which there is really this interplay between flat and hyperbolic geometry. And let me give you a couple of examples that will play a role later. So the standard examples are PSLNR, PSP2NR, and PO02, n+1. And again, I already told you what these are. So these are matrices of determinant 1 up to plus minus identity. These are symplectic matrices, so 2n by 2n matrices preserving a symplectic form on R2n. And these are going to be an orthogonal group preserving a form of signature 2n+1. And there are, of course, many more examples, but these will play a role in what I'm going to say later. And now what I want to tell you about today is something about higher-rank Teichmüller theories. And for me, a higher-rank Teichmüller theory is a connected component of the character variety that consists of injective homomorphisms with discrete image. And as before, I want you to think of this as, I mean, at least for the beginning of my talk, I want you to think about these higher-rank Teichmüller theories as moduli spaces of some locally symmetric spaces. So some Riemannian manifold, then the higher-rank Teichmüller theory as moduli spaces can be thought of as moduli spaces, as marked moduli spaces of objects of the form X mod rho of gamma. So, and if I have an injective homomorphism with discrete image, this means that I can take the quotient and I will get the Riemannian manifold that's going to be non-compact, but it's going to still be model of my surface, and it's going to have a very rich geometry because this symmetric space has a very rich geometry. Then I want this. And now I think I will write on the back. And now I want to state now a number of questions that I find very natural. So, and the first of all is, well, is this theory non-empty? So is there any other Lie group G for which I find a component that only preserves geometric interest of the representation? This is, I think, something that's highly non-clear. And I still find it, I mean, I've been working on in this theory for like 6 years now, and I still find surprising that these objects exist. So some questions that I want to address in life and I want to address in my talk today are the following. So do they exist? I mean, in PSL2R, they exist, but this might be due to compactness of this. I mean, the surface can act co-compactly on H2, so this justifies why these exist. But in general, if my group is very big, why can't I perturb my representation to lose the geometric interest? And of course, the answer is going to be yes, and it's going to come soon. But the natural next question is, why do they exist then? But I have other questions that I want to address, and are, so what are the geometric properties? Of the symmetric space X mod rho of gamma, right? So a lot of hyperbolic geometry is about understanding geometric properties of hyperbolic surfaces concerning length functions, and I mean, and you can ask a lot about the geometry of Teichmüller space, and many of these questions make sense in this more general setting, but in a sense become even more interesting because it's more strange that these objects exist, and so why should they be well behaved, and are there geometric well behavior that is encoded subtly in these theories? And the third natural question that I want to address is, do they again parameterize natural geometric structures on compact bundles over surfaces? So are there natural geometric structure on surfaces or on bundles over natural bundles over surfaces that are parametrized by these by these high-rank Teichmüller theories. So, and that is like the direction in which I want to go, and which I want to try to explore today. Okay? So and the plan for the rest of my talk is going to be that I'm going to first tell you that they do exist and give you some examples of this. I'm going to try to say something about why, and then I will give you an example in which I can say something, a concrete example, due to the work of Collier-Tholozan-Toulisse, in which you can say a lot about these two questions in a specific setting. So, to answer the question whether they exist, I want to talk about the two main families that we understand fairly well now, since 10 years, which are Hitching components and maximal representations. So the first case is when G, they do not always exist. Olivier told us yesterday that if G is a complex Lie group, is a complex adjoint Lie group, then the character variety is connected. So I have no hopes of finding a high-rank Teichmüller theory there. But there will be some subclasses of Lie groups G that admit these strange components with these interesting geometric properties. And the first class is when G is split. So in my list that is up there somewhere, you can think of PSLNR or SP2NR. Those are two examples of split Lie groups. Then if G is split, then the Hitching component so let me add something here. So if I have a split, real split Lie group, then I have the principal SL2, which is a preferred homomorphism from PSL2R into G. That is, you can think in these two examples that I care about, that I have on the board, PSLNR and PSP2NR. These are just a reducible representation. So I have an irreducible action of SL2 on Rn, and this gives me a map this gives me an homomorphism from PSL2R to my Lie group G. So this is the action on homogeneous polynomial of degree n or 2n, depending on whether I'm looking at PSLNR or PSP2NR. And I will denote this by tau. So the Hitching component that I call hit gamma G is the connected component in the character variety of the composition of this homomorphism with rho, where rho is holonomy of a hyperbolization. So I start from a point rho in my Teichmüller space, and I embed it in a bigger Lie group G by looking at this preferred homomorphism. And then I look at the connected component of this in the character variety of gamma G into my group G. And now Hitching was the first to observe the existence of this connected component, this exotic connected component that cannot be selected by characteristic classes, and proved in 92 that this connected component is homomorphic to R to the 2G minus 2 times the dimension of G. So it has the same property that the hyperbolic, the Teichmüller space had. So the Teichmüller space where R to the 6G minus 6, which is nothing but the Euler characteristic of my surface times the dimension of PSL2R. And the same is true for this exotic component in the character variety of split real Lie groups. And it was only 10 years later that Labourie, and published in 2006, showed that this is, in my definition, a high rank Teichmüller theory. In the sense that points in the Hitching component that are homomorphisms are always need to be injective and need to have discrete image. So in particular, these, for any homomorphism here, I get an associated locally symmetric space. And also, Labourie was able to say much more about geometric properties of these high-rank Teichmüller theories that I'm going to skip for the moment. But let me add a couple of keywords. So this Hitching proof was based on the theory of Higgs bundles. So an analytic perspective on the study of character variety that will be always in the back of many things that I'm going to say today. But I don't want to get into the details because I won't have time. It will take me the next half an hour to tell you the basics of Higgs bundles theory. So let's keep this as a black box. But instead, Labourie's proof of the good properties of this homomorphism was based on an entirely different area of math, which is based on dynamics. So he studied the nodes of flows associated with these representations and used that to get this surprising property. And maybe I want to add the counterpart to this last property that I have here, which is work of Labourie and Guichard that Olivier recalled yesterday, and Fock and Goncharov. Which proved that representation in the Hitching component can again be characterized in terms of boundary map. So rho belongs to hit, gamma G, PSL and R, if and only if there exists a map psi from the boundary of gamma to some good replacement for the boundary of G or of the symmetric space, which can be given in this case by either the projective space or the full flag manifold with good geometric properties. And now I won't exactly need what are these good geometric properties. Olivier described them yesterday. But nevertheless, I will need in the rest to know that going at infinity again allows us to understand a lot of properties of these high-rank Teichmüller theories. Okay? So this was the first. Yeah. It was N. Thanks. That's the standard compact space those are standard compact space on which PSL and R act. And of course, I should not have written on this board, but and of course, I should not. Huh? F is a full flag manifold. And those are the two flag space that are better adapted to study this problem. So let me get to the second case of higher Teichmüller theory that is going to play a role later, which are when G is Hermitian, which means that which are going to be my last two examples in this list, PSP2NR and PO2, N. This means that the symmetric space has a complex structure which is equivalent of saying that this is a Kähler manifold with a Kähler form omega. Right? And this was the case in PSL2R, as we can see on the models on the left in my board. And now whenever I have this thing, what can I do? I can, in order to select components of the character variety, I can pull back this scalar form and get the number, integrate it on my surface and get the number. So this is a differential 2 form that I can integrate on the surface. Okay? So then I can define a Toledo invariant to be the integral of the pullback of omega on SG, where f from the universal covering of my surface to the symmetric space is rho equivariant. So what I do, I choose a smooth row equivariant map from the universal covering of my surface to the associated symmetric space. I use this smooth map to pull back my Kähler form. This is going to be invariant by the group of deck transformation because the Kähler form was invariant and the representation is equivariant. Then this is going to descend to the quotient and I'm going to be able to integrate. And the fact here is that this is a well-defined number that selects some connected components. So a fact that I should have stated here is that if I divide by 2 pi here, this Toledo number is more or equal than the rank of G times the Euler characteristic of the surface. And I will denote maximal representation. I mean, for me, the maximal representations are going to be those connected components of the character variety for which this upper bound is achieved. Huh? This is an integer. So you can check that this is an integral characteristic class, and this is a pairing of an integral characteristic class with the fundamental class. So this is really an integer, and so this selects components. Yeah, that was something that I was swapping under drag. And so a maximal representation are going to be those for which equality are achieved. And now we have a definition, and we need the theorem. And this time was due to Burger-Iozzi, Labourie, and Wienhard, again in 06. So they proved that also maximal representations are high-rank Teichmüller theories. So again, this generalized hyperbolization is not so difficult to see that holonomies of hyperbolization are maximal for this definition. But for any other Hermitian Lie group, we get connected components consisting only of discrete, of injective homomorphism with discrete image. And again, now here, there is yet another part of math that comes into the play, which is bounded cohomology. That is going to tell me this. And again, max R, higher rank Teichmüller theory. And again, they prove that also these maximal representations can be characterized by the boundary map that they admit. So rho belongs to max if and only if, say that in max gamma G as P to an R, if and only if there exists a rho equivariant map xi from the boundary of my group to the space of Lagrangians, which is monotone. And in this case, and this monotonicity is related to the fact that for every triple of points, the Maslov co-cycle associated to 3 Lagrangians needs to be positive. So again, we have this surprising fact that we have a very big Lie group acting on a very big symmetric space. But nevertheless, I have full components of this character variety consisting of geometric representations that generalize the Teichmüller space, because again, in most of these cases, you can embed the Teichmüller space, as I was doing for Hitchin. Okay. So this finishes part 2 of my talk. Are there questions on this? So now in the question that I had down here, now we know that these exist. And now I promised you to tell you a little bit of why do they exist. And I won't have time to really tell you why. But let me keep it like this for a second. So we know that they exist. And in order to address the question why, there is work in progress by Guichard and Wienhard. Partially also together with Labourie, in which they recently introduced the notion of theta positivity. And in their work, conjecturally, they find some other higher-rank Teichmüller theories, and they explain why these exist in terms of, Lie theoretic version of the positivity reinterpretation of the positivity that is behind both the good properties of this boundary map that I have here and the good properties of the boundary map that I have up there. So this is a partial answer to this. And now in the last 20 minutes of my talk, I told you that I wanted to address these last two questions about what are good geometric properties in an example. But before I get there, I want to have a small excursus on a different tool that I personally didn't use in my research, but I find very important in the study of these higher-rank Teichmüller theories. So we have already seen a very important tool, which are these boundary maps. So these higher-rank Teichmüller theories come with this boundary map that have good geometric properties that we can understand and can be used to deduce properties, for example, of the length function associated to representation. So using this boundary map, we can construct cross ratios, and we can use theory of cross ratios, mimicking the cross ratio in projective geometry to study these objects. But I want also to talk about a more analytic, 5 minutes about a more analytic tool to study this, which are minimal harmonic map. Chalk. So I was telling you that, I think of these higher-rank Teichmüller theories, points in an higher-rank Teichmüller theory as a homomorphism, or or an action of gamma g into X. And already in the definition of this Toledo invariant, I was looking at equivariant maps from the universal covering of my surface to this high-dimensional symmetric space. But now the question is there a better equivariant map that captures more of the geometry of my locally symmetric space, or of the geometry of my action? And conjecturally, these are the minimal harmonic maps. So in order to get a better representative, the first thing to do is, one natural thing to do is to look for harmonic maps instead of just maps. And looking at harmonic maps means that I fix a conformal structure sigma on SG. So I'm fixing, if I fix a point on the in the Teichmüller space, so I fix an extra data on my topological surface, which is this conformal structure, then there exists a unique row equivariant harmonic map. F from the universal covering to the symmetric space. And being harmonic means that I am a minimizer for the Dirichlet energy. The norm of the differential. So the conformal structure gives me a way how to integrate the norm of the differential of F. And this is by work of Corlett that this always exists and are unique in this case. But so this gives me a preferred equivariant map among all the smooth equivariant maps that I have. But there's a big problem related to the fact that I'm fixing a priori this external data that is not intrinsic at all to my representation row. And in particular, this will destroy the mapping class group equivariance, the mapping class group action. This will not be equivariant for the mapping class group action on my connected component of the character variety. And for this reason, also, this map will not necessarily see a lot of the geometry of my representation, because this map will highly depend on these extrinsic checks that I don't know how to do. And now this F is minimal. I mean, it's a minimal map. So this problem can be conjecturally solved by requiring furthermore that F is a minimal inversion, which means so if my map on top of being harmonic is also conformal, so the conformal structure on the surface that I chose to define the harmonic map is the same as the induced from the Riemannian metric on X, then I get the better behaved map, which is really minimal for the area functional among all maps that are equivariant. And now a conjecture of Labourie that solves this problem of this extrinsic data of choosing a conformal structure is that if rho belongs to the Hitching component, then there exists a unique minimal equivariant minimal map. Okay? So what I'm saying is, what I'm trying to say here is that in an analytic tool to study these high-rank Teichmüller theories would be to look for minimal harmonic maps. And we expect that these minimal harmonic maps are unique. So they should see better the geometry of the representation itself. Now, this conjecture of Labourie is still widely open, is known only in rank 2. And I mean, there has been a lot of recent work in trying to solve and address this conjecture. So now this was, for the Hitching component, this was proven by Labourie in 2017 in rank 2.
In the text you write the conjecture is minimal immersion on the breadth of minimal map. Is there a difference?
No, it's the same. Minimal immersion. Yeah, in this minimal, no, this is minimal. I mean, in minimal, I mean that it's furthermore conformal. So I look at harmonic maps, and I call an harmonic map minimal if it's conformal. Right?
Ah, okay. This is just the
word.
Okay.
Yeah, that's the word that I chose for that. And conjecturally, we expect that this is true in general for high-rank Teichmüller theories, but this is widely open. And now, this brings me to the last part of my talk. In which I want to tell you something. So this will be part 4, an example, which is the study of maximal representation of gamma g in SO2, n+1, in which, due to the work of some work in Baraglia's thesis, and work of Brian Collier, Guichard-Wienhard, and Jeremy-Toulisse, we get to a positive answer to Labourie's conjecture for these classes of representation. And the reason why I want to bring this up in my last 10 minutes is because I find this work really beautiful and encodes a lot of the ideas that I just erased down here, which is in order to solve that conjecture, they pair different geometric structures. I mean, they understood the interplay between different geometric structures associated to maximal representations and use this to understand a lot of the geometry associated to these points in this Teichmüller space. So, but in order to tell you a little bit more what I mean by this, let me tell you some geometries associated to this group here. Yeah, 2, n plus 1 is the signature of the quadratic form. And in particular, this group here, I always told you that I want to think of it as the isometry of the symmetric space. These are positive 2 planes. So I take R with the quadratic form of signature 2 n plus 1. And I have the symmetric space that I can model as positive definite 2 planes for this form. And I want to think of this maximal representation as a group acting properly discontinuously on this space. Right? So that was my idea behind. And I want to find, or they want to find, harmonic maps, minimal harmonic maps in this space that are equivalent for this action. Right? But now here, I was telling you that the tool to study maximal representation or higher rank Teichmüller theories are boundary maps that are going to be valued in some parts of the boundary, which in this case would be the Einstein universe, what I call Einstein 1, n, which are isotropic lines. So this visual boundary stratifies in a complicated way, but I can find the closed SO2n plus 1 orbit, which is given by isotropic lines. Right? These are going to be singular vector, singular direction. This is going to be contained in the boundary of X. And I will have an equivariant map Xi from the boundary of gamma G. So, and this is the boundary map that I want to sort of fill in with my minimal harmonic map. But now what is the interesting idea is to, instead of looking at this space, I can look at other spaces on which this group acts. So this group also acts on a pseudo-Riemannian symmetric space, which is going to be what I call H1, H2n, which I'll draw like that. And these are negative lines in the projective space. So here I'm in the projective space of R2, n plus 1. And the group is going to act with 3 orbits, negative lines that I call H2n, the interior of this quadrant. And here I will still see the Einstein universe as a boundary and positive lines on the other side.
So do both S on 0 rather than P of 0? So
yeah, that's, I mean, I should probably write P of 0. Yeah, there is a plus minus 1. And I want to write P of 0 to get all, because not all maximal representation would lift to a two-fold cover. And now this is a projective plane bundle over a disk, this pseudo-Riemannian hyperbolic space. And again, I will see my boundary map that I want to fill on this other side. And now what they observe is that also for this, so this is a pseudo-Riemannian symmetric space. Which just means that on any point, on the tangent space to any point in this manifold, I have a bilinear form of signature 2n. And this h is because this is going to be, the curvature is going to be negative on this space. But now, and now this means that for any two-dimensional tangent plane, I can have a signature. I mean, the form can restrict to a positive definite, a negative definite over a mixed signature form. But if I restrict to space-like planes, which means that these are surfaces in this smooth manifold for which every tangent plane is positive definite. The restriction of the form to any tangent plane is positive definite. Then I can still define the energy for which I was talking about harmonic maps. Right? So space-like surfaces, one can define the energy. And what Collier-Tholozan-Toulisse prove is that there is a bijection between minimal immersions that I call fx from Sg tilde to the symmetric space that are row equivariant. And maximal immersions that I call f2, n from Sg tilde to this h to n that are again row equivariant. And in particular, they're able to translate the problem of finding minimal immersion on this side to a problem of finding, I mean, now maximal because the Lorentzian setting implies that the minimal, the critical point for that functional are maximizers for the other area rather than being minimizer. But that's again looking for, I mean, conformal critical points for the area functional. And now what they do is to translate the problem of finding a map in this rank 2 symmetric space to finding a map with good properties in this pseudo-Riemannian symmetric space that, however, in a sense has rank 1. And so the techniques that you can use to study this problem on this side are different and more powerful. And so this is the problem they managed to solve. And again, I have 3 more minutes. So this arrow here uses 6 bundles. And that arrow up there instead is I mean, you can see it from the geometry of the problem. So it's just, I mean, so this is like, if I fix, so fx of p is going to be the class of df2n of p, of dpm. Right, so if I have a space-like surface, this means that the tangent plane is a 2-dimensional subspace that is space-like. So this gives me a point in the Grassmannian of 2 planes. But I find extremely powerful. I find it extremely powerful how you can relate to very different geometries and learn from one geometry to the other. And since I have 1 minute left, I won't get to question 3. So I wanted to address this kind of questions. I told you that they exist, and I didn't have time to tell you much why, but we are working towards understanding why they exist. We discussed in an example some geometric properties, but I want to finish by telling you that something else that I learned from this non-Riemannian setup is that so now they have the solution. Oops. No. Huh? I'm saying pseudo-Riemannian, yeah. Yeah, in this pseudo-Riemannian geometry, they also get, so they find a unique conformal minimal immersion in this pseudo-Riemannian setting. But what they can also prove is that the curvature, so this means that I have this map from F to N to this pseudo-Riemannian symmetric space from this surface that has a natural now hyperbolic structure, which is obtained by the conformal structure that comes from this embedding. And now this, what they prove is that the curvature for this conformal structure is bounded above by -1. And in particular, this allows them to relate the length in this pseudo-Riemannian geometry to the length of a point in the hyperbolization in the Teichmüller space. So this allows them to say that all the length that they see when acting on this pseudo-Riemannian space are bigger than the length in the point in the Teichmüller space. And again, this tells us something about the length of closed geodesics in the locally symmetric space associated with this representation.
Is it the reason why you call it rank 1 type?
Hmm?
Is it the reason why you call it rank 1 type or something and use that word at some stage?
I mean, so that
Because of the curvature up or down?
yeah, so I mean, no, that's like this is because of the curvature of the intrinsic metric here. But and I think I will, but I find really beautiful the interplay between different objects on which the same group can act, and what this leads us to learn about different words. And I think I will stop here, and thank you for your attention.